Something that you're probably familiar with, well, in everyday language, is something called momentum. And I'm going to introduce you to the basic concepts of what is momentum. Well, it actually comes from Newton's laws, and I'm just going to break this down here. When you have momentum, well, think about this. You have Newton's second law, and I'm just going to write it as F equals ma. So here's Newton's second law. Rather than writing A, though, I'm going to write it as its original definition, and we know that A is equal to change in V over T. So I'm going to leave it like this, and I'm going to write it as net force is equal to M change in V all over T. I'm going to multiply the time across, and what I'm going to get is I'm going to get net force times time is equal to M change in V. We call this quantity right here, okay, in physics, we actually call this a momentum. And actually, the definition of momentum is lowercase p is equal to m times v. This is actually momentum. It's not power. It's a lowercase p. So lowercase p equals m times v. When you look at this here, okay, so mv, this would actually be a change in momentum because I'm changing the velocity. This is momentum. It's a vector. Momentum is a vector. Keep that in mind. It has direction. We'll talk about that in a moment. What are its units? Well, its units are going to be, let's see here, you got a kilogram times a meter per second, and unfortunately there has been no derived unit. Actually, that is the unit of momentum. It is simply a kilogram meter per second. On the left hand side, it's interesting here, you end up getting something called an impulse. Okay, this actually ends up being something called an impulse. And force times time is something called an impulse here. The unit, of course, is a Newton second, and it actually works out to be exactly the same as a kilogram meter per second. And again, it's not a derived unit. Impulse is just a Newton second. This is sometimes given a capital letter J to represent impulse. Why not I? Well, we'll see that when we get to the electricity unit. But impulse is given a capital letter J, and the unit are Newton seconds. So to create a change in momentum, you have to have an impulse. In other words, you have to apply a force over some time to change the momentum of an object. Newton originally described this whole idea of momentum as kind of quantifying motion. And so it's just giving a description of motion, and that is momentum, and it has direction. Let's take a look at some simple examples here with this. Actually, I'm just going to kind of go back and talk about this. This is actually called this formula is very important. It's called the impulse momentum theorem. You don't need to memorize this title here, but impulse momentum theory has some dramatic results. If you apply a force over time, you will change the momentum of an object. I'll discuss this more in class and some of the ramifications of this in class. What I want to spend more of my time on is talking about the law of conservation of momentum. Okay, the law of conservation of momentum. Momentum is always conserved. And the reason for it, and we'll talk about that more in class, but it's because of Newton's third law, and that every time I'm applying a force, something's applying an opposite force, and ultimately I cannot change the momentum overall unless an external force acts on a system. So the momentum will always be conserved. So what does that mean? Well, it means that if I have an object, let's say standing here, I'm going to give it an object mass m, and its velocity is 0, well, what would be its momentum right now? Well, its momentum would have to be, let's see, m times v, so its momentum has got to be 0. It's not moving. But I got another object. I'm going to make it big M. And it's moving with a speed, let's just say 10 meters per second, moving this way. Well, what's its momentum? Well, its momentum is going to be equal to, well, let's see here. You're going to get big M times v. This will be its momentum. So its momentum is equal to big M times v. This momentum is 0. Now, when this object hits this one, okay, let's suppose they stick together. Let's suppose that they stick together. Well, afterwards, you're going to get this scenario. You're going to get M and big M kind of sticking together, and they're going to move off with some, I'm going to call it v prime, some velocity in that direction. What would that be? Well, we know beforehand that the total momentum, okay, the net momentum here on this side is going to be equal to, well, m times v plus 0. In other words, adding both these up, you're going to get m times v. It means that the momentum over here has to be the same. Well, what would be the momentum here? Well, the momentum here is going to be equal to, let's call it p prime for after. Okay, I'm using little primes for after. That's going to be equal to m plus m times v prime. This will be the momentum afterwards, but it has to equal this momentum before. So if I want to figure out, let's say, the speed of these two combined afterwards, what would I do? Well, I would say, well, I'm looking for that, and I know that is equal to big M times V. So when we set all this equal, you could say, well, V prime then is equal to big M V all divided by M plus M. Nice little package. Don't memorize this again. This is for this scenario. Momentum is a vector. In other words, the momentum of this object was going, to the right. This object had no momentum, and afterwards it should be going to the right. The awkward thing comes in if they come in at angles, but angles, don't be too concerned about. If it comes in at an angle, it simply means you got to break it down into components. In other words, I'll just show you briefly here. If you have an object, let's say, okay, two objects. I'm going to call it M and big M, and this one's moving some V. This one's V is equal to 0. This is before. Afterwards, let's say they move, and here's a before scenario. Call that before, and then afterwards, what do? Well, suppose that the big M moves up in this direction. Okay, that's big M. Little m maybe moves down this direction, some velocity. And here's how to look at the scenario. Before, neither one had an upward or downward component of momentum. This one was all to the right, this one was 0. Afterwards, the momentum has to be only to the right overall. In other words, when I look at the scenario, I can tell here that this momentum in the y direction, if I break this up here, this momentum will be cancelled by this momentum. In other words, if I make up positive, that will cancel the down negative. These two will be actually equal. If I look at the x component of the momentum, okay, these ones will actually add up to the total momentum before. Okay, will add up to the total momentum before. So when you deal with laws of conservation of momentum, make sure you're giving these things direction because they're vectors. Now understand here, when I say momentum, actually just to reiterate, it doesn't mean that this speed, the upward component of speed, will be the same as this speed, but it means the product of the mass times its speed will be equal to the mass times its speed here for vertical. It has to be in this scenario because it's 0. And then the x's, the momentum of x here and the momentum of x here, they have to add up to whatever the total momentum, actually of this guy, it'll be actually equal to m times v because this is plus 0. So you get an idea of how to deal with these conservation of momentum. You'll get problems like this, and you'll also get problems maybe with a gun or a cannon. Let's say here's a cannon, and there's a cannonball inside, and let's say this is at 0 before, and here's little m, and this is big M of a cannon. Afterwards, let's say the cannon ball shoots out at some velocity v. The question will be, what does this cannon recoil at? In other words, it's going to recoil back. It has to. If you ever notice when you throw like a large ball, you end up flying back a little bit. And so what we can tell here, well, the momentum before was 0. The momentum afterwards has to be 0 for the entire system. Okay, the momentum afterwards, which means m times v, this little m times v, must be equal to m times v prime. In other words, when I add this plus this, I should get 0, and that's because maybe I make one of these negative. But it's a way to calculate certain things here. I'm not going to give these numbers. I'll do these in class, and you can work on these. It's pretty straightforward. But momentum again, you have to do m times v equals m times v prime. One last little bit of information that you should be aware of is when dealing with momentum, is there actually are several types of collisions that I want you to be aware of. And what are the types of collisions? Well, you're going to get something called elastic collisions, and you get something called inelastic collisions. What's an elastic collision? Well, sometimes in collisions the kinetic energy, okay, is conserved. In other words, whatever the kinetic energy of the objects were before, and you add them up, and remember it's a scalar quantity, that should equal the kinetic energy afterwards. This is when something called an elastic collision. An inelastic collision, okay, is where kinetic energy is not conserved. It doesn't mean that it goes to zero or anything. Please don't make that mistake. But it just means that it's not conserved. In other words, the energy is transformed to heat, to some other form, sound, some other form there besides the kinetic energy when objects collide. There is something called a total or complete inelastic. And that's an example I just did before, and that's where the objects will stick together. It's just by definition. It doesn't mean anything special happens with the kinetic energy, but it just means that the objects will stick together, and when they do stick together after they collide, we get a complete inelastic collision. This is very important, and I'll show you. You're going to have to deal with equations that look something like this. So we're going to have to look at, let's say for two objects colliding. Well, I know that for P1 before plus P2 after, or sorry, plus P2 before, so these are two objects, they have to equal the momentum after of both objects. And this is very true. In a similar way, I know that if it's a elastic collision, okay, I know that K1 of one object plus K2 of the other object has to equal K1 after plus K2 after. And this is very important. Again, realize that not necessarily that the kinetic energies of object 1 have to be the same, but the entire system has to be the same in something called an elastic collision. We'll deal with these more in class in terms of how to solve these. They can take some time, but just recognize here that K1 plus K2 is equal to K1 prime plus K2 prime, and etc. for elastic, and just by definition there of these 2 points.